Last time we started the discussion of whether a given subgraph or motif is present within an Erdos-Renyi random graph, and how the probability of its being present depends on the parameters n and p of this random graph. In particular, we are interested in what happens for large n as p scales in some suitable manner with n. So we'll continue that discussion in this lecture. So last time we ended with looking with the mention of this paradox. We looked at two specific subgraphs. So we have H, which consists of a square with one diagonal and an extra node and edge, forming a hook on it. And H prime, which looked like this, which was just the square with its diagonal. So H prime is a subgraph of H. It's contained within H. Its vertices and edges are both subsets of those of H. And then we showed the following. So we are going to consider a sequence of Erdos-Renyi random graphs indexed by n, the number of vertices. And we take the edge probability to be n to the minus alpha. Okay. So for any pair of nodes, the edge between them is present with probability n to the minus alpha, independent of all others. So this is a sequence of Erdos-Renyi random graphs. Okay, and then we showed that the expected number of copies of H okay, and we also took alpha to be 9/11. And for this specific value of alpha, we saw that the expected number of copies of H in this random graph is approximately like n to the plus 1/11th. And so this goes to infinity as n goes to infinity, while the number of copies of H prime, and this notation means equal up to constants, or bounded within constants if you prefer, which don't depend on n. So while the number of copies of H prime goes like n to the minus 1/11th, and so this tends to 0 as n tends to infinity. And in words, what this says is that, okay, or by the use of Markov's inequality, this says that as n grows large, the probability of seeing a copy of H prime in this random graph tends to 0. Nevertheless, in expectation, we see lots and lots of copies of H, and you cannot have a copy of H without also having a copy of H prime. So how is this possible? Okay, so the explanation of this paradox is that we are looking at expectations, and suppose a single copy of H prime is present in this random graph GNP, Gn n to the minus alpha. Then how many copies of H do we expect to see? So let me say that again. Okay, so let me redraw H and H prime. So let's condition on the event that G and P contains a copy of H prime, that H prime is present within a random graph drawn from this distribution. And P is n to the minus alpha with alpha equals 9/11. Okay, so if we condition on H prime, then we can get a copy of H by adding a vertex and an edge here. So this is one way to get a copy of H, and this is another way to get a copy of H. But how many ways can we choose the vertex to add here? So there are n-4 remaining vertices, and you can choose to attach them to either one of these vertices. So there are, okay, let's not worry about the fact that there are two, even let's just focus on one of these possibilities. So there are approximately n choices of vertex to go here, and then this edge is present with probability p. So conditional on H prime being present, the expected number of copies of H you see is roughly NP. Okay, and in fact, similarly here, so it's roughly 2 NP. So conditional on this event, okay, or the expected number of copies of H in G and P, given that H prime is contained within this, is at least as big as 2 times, okay, let me keep the n-4 times P, which is approximately 2 NP. Bigger or equal to, because there may be copies of H somewhere else not related to this H prime, they may be somewhere else in the graph. But you can take this particular copy, attach a vertex and an edge, and get a copy of H in this many different ways. And for each of them, there's probability P of that one edge being present. And so this is the expected number of copies you get. And now P is n to the minus 9/11. So this gives us 2 times n to the 2/11. Okay. And so this goes to infinity as n goes to infinity. So so the upshot is that it's very unlikely that there's a copy of H prime in G and P. The probability of this happening tends to 0 as n goes to infinity. But if there's even a single copy of H prime, then there's a huge number of copies of H, because you can extend H prime to H by adding one vertex and one edge. And there are n ways of choosing this vertex. And then that edge is present with probability P, and n times P is tending to infinity. Okay, so there's a dichotomy. So either we see no copies of H prime, and hence no copies of H in G and P, or we see an enormous number of copies of H. With H prime, you can see just a small number of copies, but with H, you either see nothing or you see a huge number of copies. And that's why you can have the expectation going to infinity, even though the probability is going to 0. Okay, so you can have a sequence of random variables which converges to 0 in probability, but whose expectation goes to infinity. And that's what's happening here. So let me give you one more example, not to do with graphs, just with random variables to explain what's happening. Okay, but this is the picture for the graphs. So let's now just, ignoring graphs, let's just consider a sequence of random variables. Xn is the random variable which takes values 0 or n. These are the only two possible values it takes. And then the probability xn is n is 1 over square root n. And the probability that xn is 0 is 1 minus 1 over square root n. Okay, and so we have a sequence of such random variables. Now, clearly, the probability that xn is 0 tends to 1 as n goes to infinity. And we say in this case that the sequence of random variables converges to 0 in probability. But what's the expectation of xn? It's 1 over square root n times n, which is square root n. And so this goes to infinity as n goes to infinity. So it's possible to have a sequence of random variables which goes to 0 in probability, but whose expectation is going to infinity. And something similar happens with the number of copies of the subgraph H within the random Erdos-Renyi random graph G and P. The probability that there are 0 copies is tending to 1, but the expected number of copies tends to infinity. Okay, so why did we look at this counterexample? We looked at it because we were interested in seeing whether triangles are present in G and P, and we showed, so let's go back to triangles. So we showed the following. So we are looking at a sequence of Erdos-Renyi graphs with edge probability Pn scaling as n to the minus alpha. And then we showed that in G and Pn, these Erdos-Renyi random graphs, the expected number of triangles tended to 0 if alpha is bigger than 1, and that it tended to infinity if alpha is smaller than 1. And then we also had, by Markov's inequality, the probability that there is at least one triangle, that there are one or more triangles, tends to 0 if alpha is bigger than 1. Since the expectation tends to 0, it follows by Markov's inequality that this is true. But what we would like to claim is the following. We want to claim that the probability of seeing at least one triangle tends to 1 if alpha is smaller than 1. But this is not obvious. Okay, and this is what our counterexample was meant to illustrate. Just because the expectation tends to infinity doesn't mean the probability tends to 1. Nevertheless, it is true for triangles, and now we are going to prove that. And how do we prove it? We are going to use Chebyshev's inequality, and for that we need to calculate the variance of the number of triangles. So far, we've calculated the mean, which was an extremely easy calculation. Now we are going to try and calculate the variance, which is a bit more complicated. And by the way, the method of using the mean and Markov's inequality to give a bound on the probability that a subgraph exists is called the first moment method. And using the variance and Chebyshev's inequality is called the second moment method, and that's what we are going to look at now. So we are going to apply the second moment method to triangles. Okay, so what we want to do is to calculate the variance of the number of triangles. In the random graph GNP. Okay, so let's draw a picture. We are going to start the same way. We are going to start by writing the random variable, the number of triangles, as a sum of indicator random variables. So what we do is we pick 3 vertices, or if you like, we pick a potential triangle. So we pick this potential triangle and ask whether it's actually present in the random graph GNP. Now, if we were to start with the complete graph on n nodes where every edge is present, then every potential triangle is actually present in that graph. So we are going to look at all actual triangles in the complete graph and ask whether that triangle is present in the Erdos-Renyi random graph. So meaning, are all 3 edges present? So we are going to write the number of triangles as a sum over indicator random variables. And we wrote this before as an indicator of triplets, and all I'm doing is changing notation a little bit. So we can write the number of triangles as the sum over all triangles in the complete graph, which are numbered in some way. The indicator that this particular triangle TI is present in GNP. Okay, so the indicator of this triangle. Okay, so where this indicator random variable is 1 if the triangle TI is contained within GNP, meaning these 3 edges are present, and it's 0 otherwise. I hope the notation is clear. Take some time to make sure you understand the notation. All we've done is replaced unordered triplets of nodes with triangles. So we look at all the triangles in the complete graph, which are all the possible triangles that could exist in the random graph GNP, and we number them in some way. So maybe this particular triangle is triangle number 17 in our numbering. So how we number them doesn't matter, but so we look at all possible triangles, number them, and then we are going to ask whether each one of them is present. That's this indicator random variable. And by adding up all these indicators, we find how many triangles are actually present in G and B. So maybe this particular triangle does, maybe all these three edges are in fact present. And maybe these two edges are also present. And then this edge is present. In this case, there are two triangles present. So there's a triangle, let me number the nodes, 2. So if we number these 1, 2, 3, 4, 5, 6, 7. So in this case, triangles 1, 2, 4 and 2, 4, 5 are present. Okay, and if this edge 1, 5 were present, then two more triangles 1, 2, 5 and 1, 4, 5 would also be present. But anyway, so in this particular picture, there are two triangles present. And for those two, the indicators are 1. And for all other potential triangles, the indicator is 0. Okay, and by adding up the indicators, we get the total number of triangles. Good, so that's the notation. And then we want to calculate the variance of the number of triangles. So that's the variance of this sum over all possible triangles of the indicator that that particular triangle is present in the random graph. Okay, and so what's this expression? Now, if these random variables were independent, the variance of a sum would be the sum of the variances. But in fact, they are not independent in general, and so we want to know how to calculate this. And so let me remind you of a general formula for sums of random variables. And I'm not going to prove that. You should look up you probably saw that in your first year, but if not, just check any textbook. So let me also remind you of the covariance of two random variables, x and y. So for any two random variables, x, y, discrete or continuous, the covariance is defined as the expectation of the product minus the product of the expectations. Okay, and in particular, the covariance of a random variable with itself, if you check this definition, is the expectation of x squared minus the squared expectation of x, and that's the variance of x. Okay, and then this is an elementary fact, which you can prove by expanding things out. So let me say it twice for simplicity. So if you have two random variables, not necessarily independent, then the variance of x plus y is the variance of x plus the variance of y plus twice the covariance of x and y. Okay, and more generally, if y is the sum of n random variables xi, then the variance of y is just the double sum over I and j going from 1 to n of the covariance of xi, xj. And note that you will have terms where I and j are the same, and then the covariance of xi and xi is the variance of xi. And so you can check that the first formula I've written is a special case of this. So let me also number these 1 and 2. So 1 is a special case of 2, where there are just 2 terms in the sum. Okay, so we are going to use this formula that the variance of a sum of random variables is the sum of all their pairwise covariances in order to calculate the variance of the number of triangles. Okay, so let me clear that. So the number of triangles is the sum over all potential triangles the indicator that that triangle is actually present in G and P. And so the variance of the number of triangles is the double sum over all pairs of possible triangles of the covariance of these indicators, of the indicator of triangle TI and the indicator of triangle TJ. So we want to compute for every possible pair of triangles what the covariance is. And let's do that with pictures. So here again are 7 vertices. And let's say I take this triangle here. Okay, let me draw straight lines. Okay, so here is one triangle, and here's another. Now, what's the covariance of the indicator that this triangle is present and the indicator that this triangle is present? Now, recall that in an Erdos-Renyi random graph, the presence of edges, all edges are present or absent independent of each other. So knowing this edge is present tells us nothing about any of these edges, and similarly for these two. So knowing this triangle is present and hence that these 3 edges are present tells us nothing about whether or not these edges are present. So the indicator of this triangle is independent of the indicator of this triangle. So these 2 random variables are independent, and so the covariance is 0. Okay, so the covariance for these 2 triangles is 0. Now, what about if we look not at this particular triangle, but at this one here? Okay, so I'm looking at this dashed triangle here and this solid triangle here. They have a vertex in common. Nevertheless, they have no edges in common. So these edges are again independent. So these 3 edges are independent of these 3 edges. And so again, the covariance of these indicators is 0 if you have 2 triangles with no common edges. Okay. But what happens if you do have common edges? So let me try to do that. So let's say you have this triangle here and also this other triangle here. Okay, so this edge is common to both triangles. So I'll make it a edge. So now the presence of this triangle tells you that this edge is present and therefore changes the probability of this other triangle being present. So if these two triangles have an edge in common, then the covariance is non-zero, and we have to calculate that. So that's one thing that could happen. Another thing that could happen, so let me draw it the same thing again to illustrate another thing that could happen. So we might consider two triangles with no edges in common. We could consider two triangles with an edge in common, like here. Or we might consider two triangles, Ti and Tj are the same thing. So the two triangles are sitting on top of each other. In this case, the covariance of the indicators is the same as the variance of the indicators. So that's another thing we have to calculate. So the two triangles Ti and Tj might have no edges in common. They might have one edge in common, like here. They might have three edges in common, like here. And what's the remaining possibility? They might have two edges in common. Can that happen? Well, you can convince yourselves that that's not possible. It's not possible to have two triangles which intersect in two edges, but not in three. Okay, so in principle, we have to count this, but actually, if you think about it, that pattern can never arise. So we have to consider pairs of triangles which have one edge in common and pairs which have three edges in common in calculating the variance. Okay, so let's do that. So let me repeat the formula. So the variance of the number of triangles in the random graph is the sum over all pairs of triangles Ti and Tj of the covariance of the indicator of the triangle Ti and the indicator of the triangle Tj. And so, okay, so let's calculate for every possible pattern of intersection of these triangles what the covariance is. So if the intersection of Ti and Tj has no edges, they have no edges in common, then the covariance is 0. Because the triangles are independent. And if this intersection has one edge, then the covariance of these indicators by definition of the covariance, this is the expectation of the product minus the product of the expectations. Okay, so what's the expectation of the product? What has to happen for both these? So each of these random variables takes values 0 or 1. So for the product to be 1, both of them have to take the value 1. And so the expectation of the product is the same as the probability that both both these random variables take the value 1. And if these two triangles have one edge in common, the pattern you see is this. So the number of edges that has to be present is these 3 plus these 2. So 5 edges have to be present to see two triangles intersecting in a single edge. And the probability that all 5 edges are present is p to the 5. Okay, so the indicator that both these, so for both these indicators to be 1, all 5 edges have to be present, and that has probability p to the 5. Okay, minus what's the expected value of this indicator? For the first triangle TI, 3 edges have to be present. The probability of that is p cubed, and the same for the second triangle, so that's p cubed as well. So the covariance is just p to the 5 minus p to the 6. Okay, so let me write this as a separate line. So this is, so if they have one edge in common, it's p to the 5 minus p to the 6. And let's also do the calculation if they have 3 edges in common, because that's the other possibility. Okay, so if TI intersection TJ has 3 edges, then TI and TJ are really the same triangle. They are just sitting on top of each other. Then the covariance again of these indicators. Starting with the definition, the expectation of the product. Minus the product of the expectations. Okay, so for the both triangles to be present, sitting on top of each other, these 3 edges have to be present. The probability of all 3 edges being present is p cubed. And then, as before, the product of the expectations is p to the 6. Each expectation is p cubed for this triangle to be present. Okay, so we've worked out what the covariance is if they have no edges in common, 1 in common, 3 in common, and these are all the possibilities. Okay, so now the variance of the number of triangles is the sum over all pairs of triangles, but let's now split up the sum. It's a double sum, but I'll just use one sign here to indicate that double sum, 1 sigma. So this sum is over pairs of triangles TI and TJ, such that the size of, so by the cardinality, I'll mean the number of edges, because that's what's interesting. It could mean vertices, but I mean edges. So that's the sum. And if they had one edge in common, the covariance was p to the 5 minus p to the 6, plus the sum over pairs which have 3 edges in common. P cubed minus p to the 6. Okay, so it doesn't matter where these triangles are sitting in the complete graph, so long as they have one edge in common, the covariance is the same. Likewise, if they have 3 edges in common, the covariance is the same. all this is reflecting is each edge is present with the same probability P. Good, so this is a formula for the variance of the number of triangles. So in order to calculate the variance, we have to count how many terms are in this sum and how many terms are in the second sum. Okay, so in how many ways can we pick two triangles in the complete graph which have one edge in common? So what are we picking in this case? We are picking two triangles that look like this. So what we are doing is we are picking 4 vertices. If we pick 4 vertices, okay, you can put the middle one this way or that way. So you have two choices of which edge is common. So you get, so you first have to pick 4 vertices, which you can do in n choose 4 ways. Maybe I should go on to a new page. So let me clear drawings. Do this again. So the variance of the number of triangles is the sum over pairs which intersect in one edge, b to the 5 minus b to the 6, plus the sum over triangle pairs which intersect in 3 edges, b cubed minus b to the 6. Okay, and the number of triangle pairs which intersect in one edge is essentially the number of ways of picking 4 vertices. Okay, so that's n choose 4 ways of picking 4 vertices. And then, as I mentioned, there's some constant, which in this case happens to be 2, for how many ways within the 4 vertices you can put 2 intersecting triangles. So you can decide which pair of vertices to make, so which edge is common. Okay, times b to the 5 minus b to the 6. And for the second possibility, to have 2 triangles sitting on top of each other, you have to pick 3 vertices. And once you've picked 3 vertices, there's only one way of drawing the triangle on them. So for the number of ways of picking 3 vertices is n choose 3, and then you get a constant, which in this case happens to be 1, b cubed minus b to the 6. And continuing with our sloppy approach to constants, n choose 4 is roughly n to the 4. We don't care about the 4 factorial. We don't care about the 2 here. So this is approximately n to the 4, b to the 5 minus b to the 6. And similarly, the second term is essentially n cubed, ignoring constants, b cubed minus b to the 6. Okay, so for an Erdos-Renyi random graph G and P, this is the variance of the number of triangles. Okay, and if okay, so let's take P to be n to the minus alpha, where alpha is some strictly positive constant, so it's bigger than 0. Then the variance of the number of triangles is approximately n to the 4. P to the 5 is n to the minus 5 alpha. And then let me write 1 minus p. plus n cubed. P cubed is n to the minus 3 alpha. And then let me write this as 1 minus p cubed. Okay, now as n tends to infinity, n to the minus alpha is tending to 0. So p is tending to 0. That means 1 minus p is essentially 1, and 1 minus p cubed is essentially 1. So the variance is approximately n to the 4 minus 5 alpha plus n to the 3 minus 3 alpha. Okay, so that's the variance. So we've managed to calculate the variance of the number of triangles as well as the mean. And let me remind you of the mean. The mean was n to the 3 minus 3 alpha. There are n choose 3 ways of picking 3 vertices, and there's a probability p cubed, which is n to the minus 3 alpha, that all 3 edges are present. So those are the variance and the mean. And so what? We'll come to so what in just a moment. And so let me just rewrite those formulas. The mean number of triangles was approximately n to the 3 minus 3 alpha, and the variance was n to the 3 minus 3 alpha plus n to the 4 minus 5 alpha. Okay, so let's come back to the question of asking what's the probability that there is. So we are interested in the probability that there is at least one triangle, and the complementary event is the probability that there are 0 triangles. Okay, we want to now we want to show that the probability of at least one triangle is going to 1, or equivalently, we want to show the probability of no triangles is going to 0 if alpha is smaller than 1. We are going to look at alpha smaller than 1, and we want to show that this probability goes to 0. And so we want an upper bound on this probability. And we are going to get that from Chebyshev's inequality. So first, let's look at the event that the number of triangles is 0. Now, this event is clearly a subset of the event that the number of triangles minus the mean number of triangles in absolute value is at least as big as the mean number of triangles. Okay, why is that? So what's this event? So here's 0. The mean, here's the mean number of triangles, whatever that happens to be. And here's 2 times the mean number of triangles. So we are interested in the event that the mean number of triangles is exactly 0. And that's contained in the event that the number of triangles either lies in this set, minus infinity 0, minus infinity 0, or twice the mean to infinity. Right, so if the actual number of triangles is either here, it can't be negative, so it's either 0 or it's more than twice, at least as big as twice the mean, The union of those two events is exactly the event that the number of triangles deviates from its mean by at least the mean. And so the event that it's exactly 0 is a subset of this event. Okay. So the probability that the number of triangles is 0 is bounded above by the probability that the number of triangles deviates from its mean by at least the mean. Okay, because this event is a subset of this event. Okay, and then we know a bound for the probability that a random variable deviates from its mean by more than a certain amount. The probability that a random variable x deviates from its mean by more than c is bounded above by the variance of the random variable x divided by c squared. And c here is the mean. Okay, and this bound is called Chebyshev's inequality. So remind yourselves of Chebyshev's inequality. This is exactly what it says. Okay, so Chebyshev's inequality tells us the probability that the random variable, the number of triangles, takes the value 0 is bounded above by this. And this upper bound is called the second moment method for any such. If we are not interested in triangles, but some other subgraph, there's a similar thing with the variance of the number of copies of that subgraph divided by the mean squared. And that upper bound is called the second moment method. Okay, and so we calculated this. I've written this here. So we are just going to substitute, and I have to do that on the next page. Okay, so the probability that, okay, so now let me remind you of the notation. So we are looking at G and P with P equals n to the minus alpha. And we are going to be interested in the case alpha is smaller than 1. Alpha is always bigger than 0, so alpha is between 0 and 1. If alpha is bigger than 1, we showed the number of triangles, the probability of having any triangles tends to 0 using Markov's inequality. So we've dealt with the case alpha bigger than 1 using Markov, and we are now looking at the case alpha smaller than 1. And so what we have is the probability of seeing no triangles is bounded above by the variance of the number of triangles divided by the square of the mean. We calculated the variance. This was approximately n to the 3 minus 3 alpha plus n to the 4 minus 5 alpha. And then we have to divide by the mean, which was n to the 3 minus 3 alpha whole squared. Okay, and so if you do the calculations, this is 6 minus 6 alpha in the denominator. So going up into the numerator, this becomes n to the 3 alpha minus 3 plus n to the, so 6 alpha minus 5 alpha gives us alpha minus 2. 4 minus 6 gives us 2. Okay, and alpha is smaller than 1, so 3 alpha minus 3 is negative. So this is n to a negative power, which tends to 0 as n tends to infinity. And again here, alpha is smaller than 1, so alpha minus 2 is negative. And so this second term tends to 0 as well. So the whole thing tends to 0 as n goes to infinity. Okay, because the exponents on n are negative. For alpha smaller than. Okay, so we've shown that the probability that there are no triangles tends to 0. So the probability that there is at least one triangle tends to 1 as n goes to infinity. Okay, so this is our main result, and let me combine this with the earlier result we proved using Markov's inequality and state both those together. So we've shown that the probability that the random graph, the Erdos-Renyi random graph G and P with P equals n to the minus alpha, that the probability that this random graph contains a triangle tends to 0 if alpha is bigger than 1 and tends to 1 if alpha is smaller than 1. Okay, so this says that on some suitable scaling, if we have plotted P, okay, we are plotting P as n to the minus alpha, and the probability that there is a triangle on the y-axis, then what we see is that for alpha smaller than 1, this probability is close to 1. And for alpha bigger than 1, it's close to 0. So that for large n, there's a smooth but steep transition around 1. And as n goes to infinity, these transitions get sharp, become discontinuous in the limit. Okay. Okay, so this is the main result. And essentially, this gives you the intuition for what happens, not just for triangles, but for any other graphs. There is a similar transition, not necessarily at alpha equals 1, but at some other value of alpha, depending on the graph at which there is such a sharp transition. And that's a result we'll state and prove next time. But for now, this concludes the discussion of triangles. And I'm going to stop this recording here.